This is Chapter 4, Goal 17. At this point, you have learned to graph sine, cosine with vertical stretches or amplitude changes, period changes, phase shifts, and vertical shifts. You have also learned how to use sine and cosine to sketch the graphs of secant and cosecant. And in Goal 17, we're going to learn how to graph tangent. Let's first take a look at what I'd like you to do on your own. I want you to complete this table for y equals tangent of theta and then answer questions A and B. So I'll get you started on the table and then I'd like you to finish it on your own. So I want you to find the tangent of theta when theta is equal to negative pi over 2. Now we know on the unit circle, angles are negative when you travel in a clockwise direction, and negative pi over 2 is located on the negative y-axis. We know that the ordered pair is 0, negative 1, and recall that tangent is equivalent to your y-coordinate divided by your x-coordinate, or the opposite leg divided by the adjacent leg. So in this case, tangent is negative 1 divided by 0, and we know that division by 0 is undefined. So we know that tangent of negative pi over 2 is undefined. So I would like you to pause the screencast and complete this table on your own, and then answer questions A and B as best you can. So take a moment and quickly check the y-coordinates of your table or the functional values for tangent. And then let's discuss question A. What happens to the graph of tangent at negative pi over 2, pi over 2, and 3 pi over 2? And hopefully you recognized that tangent is undefined at all of those points. So we could say that the graph of tangent would have vertical asymptotes at those 3 points. So let's sketch vertical asymptotes at negative pi over 2, positive pi over 2, and 3 pi over 2. And then I want you to go ahead and plot the other points. So negative pi over 4, negative 1, 0, 0, pi over 4, 1, 3 pi over 4, negative 1, pi 0, and 5 pi over 1. Now, I could have also had you sketch all of the 60-degree reference angles and the 30-degree reference angles. For example, the tangent of 30 degrees or pi over 6 is the square root of 3 over 3. The tangent of 60 degrees is the square root of 3. And that would have given you additional values to plot. But I felt like these would be enough. So as I sketch tangent at these points, I know that as I get closer and closer to the vertical asymptotes, the function is going to increase but not cross vertical asymptotes. Or as we travel to the left, the function will decrease but not cross those vertical asymptotes. And then it will behave in the same way between every pair of vertical asymptotes. Now I'd like you to answer these 4 questions. What do you think the period of tangent is? What do you think the amplitude is, the range, and the domain? So please answer those questions on your own, then check the screencast. Okay, well let's see what you said for period of tangent. I notice that I have a pair of asymptotes at negative pi over 2 and pi over 2, pi over 2 and 3 pi over 2. And this function repeats itself between those periods. So I would say that a period repeats itself following a pair of asymptotes. So now we need to figure out how far apart are those asymptotes. Remember, you can find the distance between two numbers by subtracting those numbers. So I'll take pi over 2 and subtract negative pi over 2. And when I add, I get 2 pi over 2, which is a distance of pi. And I'm just going to double check that by also subtracting 3 pi over 2 and pi over 2. So I'm subtracting consecutive asymptotes. And when I subtract, I do see that my asymptotes for tangent are pi radians apart. So a period of tangent is different than sine and cosine. A period for tangent occurs every pi radians, or every 180 degrees. So we can say that the formula for the period of tangent is not 2 pi over b, but 1 pi divided by the absolute value of b. And so you'll need to make note that the formula for period of tangent is different than sine and cosine. All right, so what about the amplitude? Remember, the amplitude is the height above and below the x-axis, or the distance that the function rises above and below the x-axis. And you can see that tangent has an amplitude that goes from negative infinity to positive infinity. So it does not have a max and a min. But I do want you to notice that in this function, y equals the tangent of x. A is 1. And if you notice, halfway between the midpoint and the asymptote, the function reaches 1, and halfway between the midpoint and the left-hand asymptote, the function reaches negative 1. Again, if you look at the period between pi over 2 and pi, the midpoint's at pi, and halfway between pi and 3 pi over 2, I didn't draw that clearly enough, and I should have, I apologize. The function reaches a value of 1. Halfway between the leftmost asymptote and the midpoint, the function reaches or crosses through negative 1, or the negative value of a. So you can see halfway between the midpoint or at the quarter marks, tangent is equal to positive a, in this case 1, and negative a, in this case negative 1. So you'll need to make a note of that tangent hits positive a and negative a at the quarter and 3/4 marks. So what do you think the range of tangent is? And clearly you can see that that's from negative to positive infinity, or that the range is all reals. Now the domain's a little bit trickier. So we've only sketched 2 periods of tangent here, but if we know that the period length is pi radians, then we should be able to sketch some additional periods. So if the period length is pi radians, that means that we should have a vertical asymptote every pi radians. For example, pi radians to the left of negative pi over 2 is negative 3 pi over 2. So we should have another vertical asymptote. If we divide this into 4 equal parts, the halfway or our midpoint between the asymptotes, we should cross the x-axis. And you see that in the first 2 periods we sketched. And then at our 3/4 mark, we should be at positive a, and our 4th quarter mark, we should be at negative a. And you can see that we have another period for tangent. So what can we say about the domain? I notice that the domain is all reals except every time I have a vertical asymptote. And if you look at these vertical asymptotes, they all have denominators of 2, but numerators that are negative 3, negative 1, 1, 3. If we continue to the right, the next vertical asymptote would be at 5 pi over 2, then 7 pi over 2, then 9 pi over 2. So I'm noticing that the domain is all reals except odd multiples of pi over 2. And if you think about that, on the unit circle, if we look at our ordered pairs at 0, pi over 2, negative pi, and 3 pi over 2, tangent is always undefined when our x-coordinate is 0. and that's at pi over 2 and 3 pi over 2. So when our x-coordinate on the unit circle is 0, tangent will be undefined, and that always occurs at 90 to 70 or pi over 2 and 3 pi over 2, or variables of such. We're going to practice sketching 3 periods of tangent. We're going to begin just like we would sine or cosine and identify A, and in this case, the coefficient of tan 2x is 1. We'll identify B, the coefficient of x is 2. There is no C, there is no D. So I know that I will have this A value will come into play, and then B equals 2 helps me calculate the period. Remember for tangent that period is pi divided by the absolute value of B, or pi over 2. That means that every pi over 2 radians I should have a new asymptote. Okay, so to help you see what's about to happen, this means that these asymptotes that occurred at negative pi over 2 and positive pi over 2 are going to have to shrink in closer together. Or the asymptotes at pi over 2 and 3 pi over 2 are going to have to shrink closer together. So right now we are going to choose negative pi over 2 and positive pi over 2 as the asymptotes for the parent function of tangent. Let me say that again. We are going to choose the parent function asymptotes for tangent as negative pi over 2 and pi over 2. So to help us calculate our new asymptotes when the period shrinks or stretches, we will take bx minus c and place it between negative pi over 2 and pi over 2. Just like we did with phase shift when we were dealing with sine and cosine, we will do this for every function of tangent. So I've taken bx minus c, 2x, and placed it between the asymptotes for the parent function. Notice I did not place an equals under the inequality symbols because we cannot equal an asymptote. So to isolate x, I'm first going to multiply the entire function by 2. Actually, I'm sorry, I'm going to divide by 2. Remember that division by 2 is equivalent to multiplying by 1/2. And now our asymptotes are at negative pi over 4 and pi over 4. The distance between negative pi over 4 and pi over 4 should match our period. Let's double check. If we subtract pi over 4 minus negative pi over 4, we get 2 pi over 4, which does indeed reduce to pi over 2. All right, so let's sketch this function. I will still label my a and negative a on the y-axis. Because my asymptotes are at negative pi over 4 and positive pi over 4, I will label both of those asymptotes on the x-axis, and then I will draw those vertical asymptotes. Now, if you go back and analyze the parent functions for tangent, remember that we will divide this into 4 equal parts, the halfway, or the midpoint, and the quarter marks. And tangent is at negative a, the midpoint, and positive a. To sketch a second period, we would always add the period to the endpoint. Pi over 4 plus pi over 2. We want a common denominator of 4, so that is 1 plus 2, or 3 pi over 4. And we'll divide it with our quarter marks, and then we are at negative a, midpoint, positive a.